All right. All right. Good evening, everyone. You want me to turn off the front light or turn on? Turn it on. Is this one better? Okay. So let me share my screen. Well, so we're gonna today we will try to finish this chapter, and after we have finished this chapter, we basically have finished the part related to image processing in this course. And after that, we will move on to study the contents related to deep learning and vision. Okay, so for the first few lectures are they're more relevant to image processing so far. They're more relevant to image processing, but of course, the convolutional filters, all those concepts are fundamentals for CV. And we will do another lab session, another lab assignment next week, the image stitching task. Okay, so in last week, we briefly introduced local invariant features. And we also talk about if we want to do image stitching or image matching, then we should be able to identify some local features that the local features which have the following properties. So one, which is perhaps the most important one, is repeatability. What does it mean? It means it means the same feature can be identified. The same feature can be identified in the same feature can be identified independently from different images. For example, this feature can be identified on the left image, while this feature can be identified on the right image. Identifying the same features from different images. That's called repeatability. For example, this. Okay, you see? These the little two patches, they represent the same features. Well, what do we mean by feature? We're gonna represent this local patch using a vector. For example, 128 dimensional vector descriptor, and we call that a descriptor. And as you can see, the sizes of the two patches are different. So exactly, we want to introduce how can we undo the scaling effect, undo the scale, and also their rotations are different. Okay, so we want to how can we adjust the differences in scale and orientation. Okay, so these are the features we want to identify for completing tasks like stitching or image matching. Okay, so that's what we mean by repeatability, because we can find the same patch, which we call local features, from different images. Okay, the second one is different features are different, have a different representation or different description. Of course, we want to represent different the image patches. Different image patches should be represented differently, of course. Okay. Otherwise we will match. We cannot do the right match if they are represented by the same vector. Okay, so this is natural. We want the distinctiveness. And for the following, we want a relatively short vector. And also, we only want to identify. For example, given an image, we only want to identify like a few hundred, or just a few hundred interest points, because those features should be much less than the number of image pixels. So there are many image pixels. So given a 300 by 400 image, the number of pixels is equal to this number. Okay, but we should represent this image with perhaps only 100 interest points. Okay, we using only 100 interest points, and each point is represented by a vector, or 128 vector. Okay, so that's what we mean by compactness and efficiency. And lastly, a feature, because they are local features, they only occupy a relatively small area like this. So a feature only occupy a relatively local area. That's why they are called local features. Okay. So basically, these are the desirable properties of local features. And we want them to be able to, and we want those features to be robust, such that we can, to be robust to some transformation, for example, rotation and the scaling, just as we mentioned, scaling and rotation, such that we can identify because those features are robust to scaling, and rotation. What do we mean by robust? For example, for this image patch, okay? It means that we can identify. Remember the repeatability we just mentioned. We can identify the same feature across different images. And then how can we do the matching? We must undo the scaling effect and also the rotation effect, and we can match them. You know, we can when we undo the effect. You know, we can all this the two different patches, after we undo the scaling and orientation effect, we can map them, or we can transform them to be this standard patch, and then they are represented in roughly the same vector by roughly the same representation. Okay, so that is basically what Sieve detector does. First, we do detection, identify those interest points, and then we represent these image patches by removing their scaling and the orientation effect, so they can be represented by the same feature. Okay, so geometric transformation means scaling, orientation, rotation. Photometric transformation means changes such as illumination or shadows or highlights. So we're going to see later that the SIP detector is robust to geometric transformations, including scaling and rotation. And it's also robust to illumination. And okay, repeatability. So this slide shows the importance of repeatability. So if we want to, stitching two images, we should be able to, the algorithm should be able to detect at least some of the same points in both images, so we can connect them. Okay. If you run an algorithm and you identify two totally different set of key points, then there's no way you can combine the image. You can match the image, right? So repeatability, identify the same key points from different images. Not all the same, but because there are some overlap between the two images. So if we run the algorithm, the key points identify the algorithm, there should be an overlap between the two sets. Okay, because the image features, the image contents are the same. Not exactly the same. There are some overlap between the two images. Okay. So you have to be able to run the detection algorithm independently for each image, and they can find some of the same points. Well, this slide shows different key points should be represented differently, which is natural, which is so this look at these image patches. They are represented by so if we're gonna represent these little patches into vectors, then the 4 patches, they should be represented rather differently because their contents are different. The image content are different. However, this image patch, this one is similar to this one. So their representation should also be largely similar. Okay. And we have already mentioned that geometric, photometric. Geometric changes means rotation, scaling. Photometric changes involve lightening, illumination changes. Okay. And we also talk about interest point. What are interest points? I want you to maybe watch this lecture, blobs as interest points.
Want to trade CME Group futures at a low cost? Access a wide range of CME Group futures with Interact.
Now let's take a look at what really is an interest point in an image. Let's take a look at this object right here and 2 images of it taken under different conditions. If you consider this patch right here, this local area, you see that there is a difference in size because the magnification used is different in these 2 cases. There's of course a difference in orientation, in lighting for sure, perhaps the distribution of light, but also the intensity of light, and so on. So any interest point detector that we want to develop should be able to.
So take a look at that. If we want to match them, the two patches, they have different scaling and orientation, as well as illumination, lightning changes. Okay, so we are going to so our detector should be robust to these factors. Okay, so let's see.
Compensate for or remove for these variations. Only then can it match a feature in one image to a feature in another image. And so if you consider this patch that we were looking at earlier, you see the differences right here. We want to be able to somehow normalize or compensate for scale differences.
So we compensate for the scaling if we enlarge this one.
Rescale one so it matches the scale of the other. We want to be able to reorient one so it matches the orientation of the other. And we also want it to be more or less insensitive to brightness and lighting changes as well. So in other words, matching features or interest points becomes easier if we can remove variations such as size and orientation. And when you develop an interest point detector, you also don't want it to respond to a lot of things in the image. There are a lot of patches in an image that are simply not interesting. There is stuff going on here, but it's not unique and interesting enough to actually detect and use for matching purposes. So all that said, what are the desirable attributes of an interesting point or feature? Well, first, an interesting point has to have some rich image content around it. The local appearance around this point should be rich enough in terms of brightness variations, color variations, etc., that there is a certain amount of uniqueness to it that can be exploited for matching purposes. Second, it should have a well-defined representation. What that means is that from this appearance in this local window, we should be able to compute a signature that we can then use for matching purposes. And it has to have a well-defined position, because ultimately when you recognize things, you also typically want to know where they are. So position is very important. It has to have a well-defined position in the image. It should be invariant to image rotation and scaling. So if you want to find things under arbitrary rotations and scales, the interest point itself should be able to produce a signature that finally is invariant to image rotation and scaling. And finally, it should be insensitive to things like lighting, as we mentioned before.
So we have talked about the last two properties. Well, as you all know, we consider blobs as interesting points. Blobs has a well-defined center blob, center of a ball, and it has a well-defined. We will see later. What is this signature function? The signature function of blob, and it has rich image content. So what is a blob? So blob, it doesn't necessarily have a round shape. It could have a square shape. So blob just means regions which are brighter or darker than the surrounding area. Regions which are brighter or darker than surrounding area. Roughly speaking, that's what blobs means.
So all this said, with this list of desirable attributes, the question again is, what then would be a good interest point? So first question, the obvious one, are lines and edges good interest points? Well, let's take a look at that. Here you have an edge in this image. This is an image of a scene. This is a slightly more close-up image of the same scene. And here you have an edge here, and we already know that edges are rapid changes in brightness within a small window, and that's what you see here. You have a rapid change. And the question is this interesting enough? And unfortunately not, because when you look at this image, you're going to see lots of edges there that have the same kind of brightness variation. And so the problem with edges is that edges really slide along boundaries of objects, and they look pretty much the same as they slide. They're not really descriptive enough and unique enough to be used as interest points. Now, this might lead you to believe that perhaps corners are good. And indeed, corners are interesting interest points. And
So indeed, corners are more interesting. Corners are more interesting than edges. What is a corner? A corner is where two edges meet, right? Two edges converge. So corners are easier to locate or identify than
they have been
edges.
used as interest points in the past, but for simpler applications, not for recognizing complex objects, because corners just don't show up that often and by themselves are not very unique features.
So compared to blobs, corners are not as interesting because they are not that unique.
So now let's take a look at something else, which is blobs. So here you have a region in this image, right here, this blob, and here is the same blob in this image. And now,
so let's look at this closely. Well, it doesn't have a round shape. It's a square. So what we mean by blob here is that it's a region. It's a region which is brighter than the surrounding areas. Okay.
after you normalize for scale and you put them in windows of similar size, they look like this. And what's interesting here is that you have some kind of a local appearance in that there's brightness variation going on in here. And that defines the appearance of the blob itself. And also the position of the blob is very well defined. So yes, blobs have a fixed position and may have some interesting appearance within it, and therefore could be potential.
Where is the position of the blob? Well, it's the center of the blob. The center of the blob is the position of that blob. So unlike edges, blob has a fixed position. Edges don't have a fixed position, right? Well, blobs has a definite size. It has this is the size of this blob. While edges don't have a definite size.
Actually, very good interest points. So we're going to do exactly that. We're going to use blobs as interest points. And so for a blob-like feature to be useful, we needed to have certain attributes. First, we need to be able to locate the blob. That is, there should be a position associated with it. The position doesn't have anything to do necessarily with any particular feature in here, inside the patch. It is a position that emerges from the way we actually do the detection of blobs. And then it has to have a size associated with it. Size, again, is a very interesting concept in this case. It has nothing to do with edges or boundaries of the appearances or the various visual artifacts that you see inside of the blob. It's just the rough scale of this appearance itself. It's a fairly abstract concept in this case, the size of the blob. And then you have, of course, an orientation associated with the blob, because the blob itself can appear in different orientations. So we need to be able to compute a principal orientation of the blob. And finally, we need to be able to, after we have done all of this, extract a description or a signature which relates to the appearance inside the blob itself. This signature is very important for matching purposes, as we mentioned.
So the signature is the vector description, the standard vector description of this, the content of this such image content. What do we mean by standard description? The signature is just the this. We have a signature vector, this vector, which describes this standard, we call it standard patch, whose scale and size, whose size or scale and orientations, it points to the normal standard orientations. Okay. Okay. So that's the interest points. That's what we mean by blobs. It's just a local area that is either brighter or darker than surrounding areas. Well, in SIFT detector is designed for identify SIFT is designed for identify blob-like features, blob-like feature points. Okay, but we will start with corner. Okay, we'll introduce corner detection first. So we have introduced edge detection. Now we're going to introduce corner detection. So corners are places where two edge converge. So similarly, well, let's recall what are the techniques or what are the metrics we used for edge detection? What do we use for edge detection? How can we identify edges within an image? How to identify edges? We use what? So edges are where there are significant changes in what? In pixel values, right? There are significant changes in neighboring pixel values, brightness or colors. So we do edge detection based on what? Based on, so what describe the changes? What are used to capture changes in image pixels, the image pixel values? So you haven't done your homework? The lab assignment. We use what? For how to do edge detection. How to do edge detection? How to identify an edge? Should we use gradient magnitude? Well, remember, let's recall when we want to identify horizontal edges, and we can identify vertical edges, right? What do we use? We use image what gradients, okay, by comparing, because edges are just edges occur when there are significant changes in image pixels. To identify such changes, we need to compare the differences between neighboring pixels. You get the idea? If you want to identify edges, you need to compare the values of neighboring pixels. Okay, that's the idea. And those differences are captured by what? By image gradients, x derivatives, and y derivatives. As simple as that. Okay, so basically, changes in image content can be captured by what? By derivatives, by image derivatives or image gradients. Okay, so similarly here, we're gonna apply image gradients or derivatives to identify corners. Okay, corners are more complex than edges because corners involve two edges. Okay. So here, we have a very simple image. And within the image, you can easily see there's a corner. There's a corner here, right? There's a corner here. Well, for corner detection, the goal is to identify the corner points. The corner points, which is represented by this red dot. This is a corner. This pixel represents a corner. Okay. So this is our goal. Well, within this image, you can see there are some flat regions. The black region is a flat region, and so is the white region. Okay, so if you place a window within the white background, the white background is a flat region, and the black foreground is also a flat region. By flat region, we mean if we're shifting a small window in any direction within the flat region, if we shift a window, for example, this one, in any direction, there will be no change in image content or image intensity. We call it flat because the image contents are pretty much the same. Because if we move the window along any direction, there won't be a significant change in image intensities. Okay, so clearly the background, both the white background and the black foreground, they are flat region. However, if we slide a window, along the edge, what will happen? If we slide this window along the vertical edge, Is there any change in intensity? There's no change. The image content is also within the window is also the same. Okay, and so and the same thing happens if we slide the window, this window, along the horizontal direction, horizontally. Nothing changes. Okay. But what if we move the window not along the edge direction? What if we move the window along the direction that is perpendicular to the edge direction? What if we move the window horizontally? Is there a change in image content? The image will look very different if we move them along this direction or this direction, right? Then what's different for corners? So if we place the window at the corner position, which means the center of the window is a corner point, what happens? If we place this small window at a corner position, you can see that. So recall we have said that corner is the convergence of two edges. Okay, so it's like a corner is determined by, two independent vectors. Okay, so in this case, if you move the window in any direction, will there be a significant change? Yes. So if your window is at a corner position, then there will be significant changes in all directions. But if your window is only at the center of your window is only at the edge, is only an edge point. If the center of your window is at the edge pixel, if this is an edge pixel, then because edges are one dimension, then there won't be any change if you move the window along the edge direction. But there will be significant change if we move them along the direction that is perpendicular to the edge direction. So that's all about corners. Then so after this introduction, can you develop an algorithm to detect corners? Well, we have algorithm for edge detection, right? We have algorithm for edge detection, which are not difficult. Just apply image gradients, comparing neighborhood image pixels. Then we can identify, by applying to deal with noise. We apply what? Sobel, derivative of Gaussian, Sobel operator. And we also remove redundant edge pixels using non-Masterman suppression. Okay, etc. Then what about corners? How to identify, for example, this corner point? Within this image, they may be the size of let's say the size of this image is 100 by 100. Then they are 10,000 pixels. 10,000 pixels from these images. And we want to identify those pixels, which are corner pixels, which represent corner pixels. And essentially, if we do non-Masterman suppression, ultimately there will be only one pixel, which represent corner, because there's only one corner within this image. Okay, so we're gonna select one pixel from those 10,000 pixels, which represent corner. Okay, so you can imagine we do corner detection by basically by sliding a window across the image, and then we compute something, and then we look at the content within this image, within this window, and we somehow do some computation, and we can identify. We come up with a metric which measure the cornerness score for each pixel. Okay, so let's just skip all the mathematical details and take a look at the Harris corner detection algorithm. Okay, so basically, we slide a window. We slide a small window across the image. We place this window at each pixel, at the position of each pixel. And for each window, which is for each pixel there's a window, right? For each window, we compute some matrix. And then we obtain a cornerness score for each pixel. Okay, say we have two images. And we slide a window, for example, this window across the image. We scan the image in this way. And we do the same for this image. Okay, so we scan the image, and for each window or for each pixel, we compute a cornerness score, a corner response. And if we visualize the response using a heat map, so a heat map means it's always represent the red color. Red color means, for example, 1, response 1, and the blue color means cornerness, well, corner response 0. Okay, so if we slide the window across the image, then we will obtain a corner response map like this. And then we can do what we can do. Because we want to identify corners, we should focus on pixels with high response. So just as in edge detection, let's set up a threshold, right? Let's set a threshold. So we find the points with large corner response. And this is what we obtained. But as you can see, just as in edge detection, we obtain multiple response. There's some redundant responses. Redundant response, well, which means, for example, we obtain, for example, there are multiple points with high response for this corner. Then what should we do? Multiple points that are with high response. What do we do in edge detection? What do we do for edge detection? for edge detection, after we compute the gradient magnitude map, remember what we do? There are some thick edges, right? There are some thick edges, and we want to do thinning, which is to remove the redundant edges. Remember, in edge detection, we perform non-maximum suppression to remove the redundant edge pixels. See? So this is the gradient magnitude map. In edge detection, after we compute the gradient magnitude map, we observe that there are some redundancy, thick edges. Then we perform non-maximum suppression to assure minimal response. Okay, so before non-maximum suppression, you can observe the thick edges. There exist those redundant edge pixels. After non-maximum suppression, we obtain unique response for each edge. So similarly, we want to do the same for corner detection. Okay, so after we thresholding the corner response map, we obtain corner pixel map. Okay, and those white pixels represent the pixels with high response, with high corner response. But there are many, because we want to assure minimal response, unique response, minimal response. So we do non-maximum suppression by only keep the point with local maxima. For example, we only keep one point. We only keep the largest response for this region. Okay, and this is our final corner map. And those white pixels just represent corner points. Okay, so that's how we do corner detection, and we skip like all the mathematical details, but that's our detection algorithm. So in the following, we're gonna explain how to compute the cornerness score. And basically, we will look into the image content within each window. And this involved the computation. Once again, I would like to emphasize that this involved the computation of what? Image gradients. Just as in edge detection. Image gradients. Okay, now let's take a 10 minutes break. All right. Now, so it seems a lot of you are sleepy. Okay, so feel free to eat. It's okay. It's okay to eat during during the class. That's okay. So so remember when we talk about corner detection, we say the algorithm looks at the image content within a window. Well, that's what it does. It computes a matrix M. And we will talk about later about what matrix M is. But basically, it looks at the image content within each window. Okay. Now, let's say here is the center of the window, and here is the pixel for this pixel. Okay. The red one represents the current pixel. And if we look at this window, the image content within this window, what can we observe? It's all dark. It's all dark. What about its image gradients? What about the image derivatives within this window? For each pixel, let's consider its x derivative and y derivatives. Let's consider the x derivative and y derivatives for every single point, for every single pixel within this window. Let's consider its x derivative and y derivatives. And what can you observe? They're all zero. They're all zero because the image content is basically the same. There's no variation. Okay, so the x derivatives and y derivatives are all zero. Then what about this one? The y derivatives are all zero, right? Right? The y derivatives for every single point, for all the pixels within this window, their y derivatives are zero because there's no changes along the vertical direction. Every column is the same. Okay, but it's not the case for x derivatives, right? It's not the case for x derivatives. And what about this? Well, this one is much more complex because for there are some points where whose x derivatives are not zero, and there are some other points whose y derivatives are not zero. Okay, so 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 that's the idea, but we will use some quantitative metric to because we cannot, because we cannot examine their x derivative and y derivative one by one, right? We're gonna design some metric to examine all the derivatives holistically. Okay, so that's how we do. That's how we do it. Well, let's look at the content within this window. How we quantify the changes. How we quantify the changes. we quantify the changes by, let's say, if we move the window for some small amount represented by u and v. U and v is a vector. So if u is 0 and v is also 0, then there's no shift, right? Well, no shift means there's no change. There's no change in the pixel values. So E00 is 0. When U and V are 0. Right? You know, what does it mean? So why do we want to examine for this trend? Why do we want to shift the window for some small amount? Because we want to quantify the changes. Like we mentioned before, we want to know how the derivatives, how the image derivatives are within the window. We need to have some. We want to design. We want to understand. We want to understand how well, as we mentioned before, we can roughly know whether this point is represents a flat region or an edge or a corner by looking at its image gradients, right? By looking at its image gradients. But it's not easy to just can you differentiate this case with this case? Because there are some non-zero. There exists some non-zero image gradients, because we need to design a more convenient way to tell whether this point represents an edge or a corner. So that's why we want to see how the image content will change if we move the window, if we shift the window for a small amount. Okay, so if we move the window for a small amount, U and V, if there's no change along any UV direction, then it represents flat region. And conversely, if there is a significant change along any UV direction, then it represents corner. Okay, and in between is that there might be a significant change along one direction, but there's no change at all along the other direction. Then it represents edge. Okay, so that is the idea. That's why we want to examine this quantity, EUV. Okay, now we will compare what's the pixel value within this red window and those within the green one. Say if we shift the window by U horizontally by 3 pixels and vertically by 2 pixels, right? So the window is shifted from the red position, the red one, to the green one. Okay, then there that their change in appearance, their change in image content can be measured by this pixel value minus the corresponding one after shifting. Okay, so let's measure the differences between this value and this value. The squared difference. The squared difference. Okay, so we do this for every single pixel. That's why we have a summation with respect to every single pixel within the red window. Okay, so that's how we measure. That's how we measure the changes in image content between the original one, the original window, and the one after shifting, the shifted window, the original window and the shifted window. So we restrict the shift to be small so we can quantify these changes using image gradients. Okay, so that is the idea. And actually, EUV here, this is a visualization of this function. You can see for E, this block represents E00. So it's completely dark. Remember, this is a visualization of this function. So E00 represents this block represents the value of E00. And this one just means the shift is 0, no shifting. Therefore, there's no change in image content. Okay, and similarly, this one, E32 represent E32 represent the changes between the red window and the green window. Clear? E32, this one, represent the changes between the red one and the green one. So this is the visualization of well, for any other block, and for example, 1, 2, 3, this one, this block represent E03, okay, and this represents the changes between the red window and the blue one. The blue one is by shifting the window upward by 3 pixels. Okay, so E03 represents the difference between the original red window and the blue window. The difference in image content. Okay, so this is a visualization of this function. Remember, we can compute any EUV for any UMV. Okay. So this is the key function. We want to quantify the changes of image content along any direction, where the direction is represented by U and V, because it's 2-dimensional. We can move this window along any UV direction. Okay, along any UV direction. Now let's take a look at the mathematic. How can we compute this? How to compute this? And once again, we only measure the small shifts, because we want to be able to use image gradient to represent these changes. Well, that's for one. For another is we don't want, if UV is too large, we only want to shift the window locally. Okay, we don't want to shift this window, for example, from this position to here. If we shift the window here, of course there will be a significant change. So we only want to shift the window locally to examine its changes. Okay. So that's how we derive the changes. We use Taylor approximation, first order Taylor approximation. So we assume this is a two-dimensional function with respect to x and y. X, y are variables, and u and v are, let's say, delta x, delta y. Okay, and this one can be approximated by, Taylor expansion. This is the first order x derivative, y derivative. Okay, because when u and v are small, we have Taylor approximation. We have Taylor approximation because u, v are small, then we can approximate this function using its first order derivatives, x and y. That's Taylor approximation, Taylor expansion with first order Taylor approximation. Okay, then we plot this. We plot this to represent this item. And conveniently, very nicely, you can see these two terms just canceled out. And what's left are Ix and Iy. What are Ix and Iy? Ix is the x derivative. Iy is the y derivative. Okay, so this term can be computed. If we expand this, it can be computed like this. So for any pixel, xy represents the coordinate of any pixel within this window. For any pixel xy, that's the coordinate of the pixel. We need to compute this. We need to compute, for any xy, we need to compute its x derivative. X derivative, the square of x derivative times u square, and Ix, Iy, x derivative times y derivative, and the square of y derivatives. Okay, so now you can see these changes. This change function. This change function can be fully described by what? It can be fully described by the image derivatives within this window. That's how we quantify. That's how we quantify the changes. We're not done yet. Okay, we're not done yet. But let me show you what Ix and Iy is. So given this image with, there are squares, multiple shape, and the lines, Ix is the map of its x derivative. Well, you can see, as we mentioned, x derivative are good for capturing what type of edges? Vertical edges, right? X derivatives capture vertical edges. See? Okay? And similarly, y derivatives are good for identify horizontal edges, right? Then what is Ix times Iy? Ix times Iy is just the multiplication of the two derivatives. Okay? So the summation of Ix times Iy can be computed like this. So we have, this is Ix. This is the map of Is. So for within this window, for each point, for each pixel, we compute its x derivative. So this is the matrix of x derivative. And this is the matrix of y derivative. For each matrix, we compute its y derivatives. Okay, so this term can be computed by, by a pairwise multiplication of the two matrices. So this element will be multiplied with this element, and this element will be multiplied with this. Okay, a pairwise multiplication of the two matrices. And then we obtain this multiplied. We obtain this new matrix, and then we sum up each element within this matrix. So that's how we compute this term. Clear? That's how we compute this term. So so now you know. So I want to explain how to compute this for every pixel within the window. Okay, for every pixel within the window, we can either compute this term for every pixel within the window, or we can do this, or we can do it separately. Okay. Okay, so like we said, for every pixel within the window, we can compute this term for every pixel within the window and then sum them up, aggregate them together. Okay, or we can do it equivalently. We can compute this term and individually compute the three terms individually. And after some manipulation, this one can be represented in this matrix form. In this matrix form, see, we can write UV as a row vector, and this is UV as a column vector, and you can check this quadratic term is equivalent to this term. Okay, so essentially the computation of EUV boils down to the computation of this quadratic term. And, you know, UV are variables for any UMV. For any UMV, so the signature of this function is determined by this matrix, which we call second moment matrix. Because UMV are variables. UMV are variables. So this function is given. This function is characterized by this matrix M. So it turns out this matrix M contains all the information we need to identify whether this point is corner or edge or flat region. Okay, so the second moment matrix M is the key to corner detection. Well, let me ask you a question. What's the dimension of this matrix? What's the dimension of this matrix? Is it, let's say the window size. Suppose we have an n by n window. The window size is n by n. So what is the dimension of this matrix? Is it n by n? Come on, we only have two-dimensional vector. And this is also a two-dimensional vector. So what's the size of this matrix? 2 by 2, right? This is a 2 by 2 matrix. Okay? And this, what is this? This is a function with two variables. This is a function with two variables. And the output of this function is a scalar. It's a scalar because you measure the changes between two windows. The output is a scalar. Okay? So this is a 2 by 2 second moment matrix M. Well, let's evaluate. Let's examine the characteristics of this second moment matrix M. So first of all, this element is only related to the x derivatives, right? X derivatives. While this element is only related to the y derivatives. Okay? Well, for the off-diagonal terms, the two off-diagonal terms are exactly the same. So this matrix is symmetric. This is a symmetric matrix. Okay? Now let's take a look at what happens when this window is within a flat region, meaning that every pixel has the same value. What happens? What happens if the current window is within a flat region? All 0, right? Because Ix, Iy, they are all 0. Now let's think about what happens when this window is placed along one of the edge. Well, consider on this case, if the window is placed here, so for this case, all the vertical, all the columns have the same pixel value. So for all the y derivatives are 0, right? All the y derivatives are 0. Then we know this one is 0. This one is 0. correct? Then what about this? This is non-zero because there are some points with non-zero x values, x derivatives. So this one is non-zero. Okay. So what we have is there is some value which is non-zero, but there's a 0 here. Then what about this term? That's why I want to explain ix and iy. The computation of this one can be it can be computed like this. So we have a x derivative map and y derivative map, and then we multiply them pairwisely. So I would like you to observe this map. Okay, for a corner pixel, sorry, for an edge pixel, for an edge pixel, all the y derivative iy is 0. Then what about ix? Well, at least for those pixels, their ix are non-zero. For these pixels, their ix are non-zero. However, since all the iy are 0, which means this is 0 because all iy are 0. Clear? So this is the case for edge pixel. And if we place our window here, and you can observe all the x derivative ix are 0, but some iy are non-zero. Okay, so what would be the second moment matrix? What will the second moment matrix M be like in this case? In this case, because all the ix are 0, this term should be 0, right? And because there are some iy are non-zero, so this term is non-zero. Then what about the off-diagonal terms? They're all 0. Okay, so that's how we know that when the second moment matrix be like this or this, then they represent edge pixel. If they are all 0, then it represents flat region. For corner pixels, because ix and iy, there are some ix and some iy are non-zero. So for corner pixels, the two diagonal terms are non-zero. But what about the off-diagonal terms? The off-diagonal terms, for the off-diagonal terms, is it also 0? For the off-diagonal terms, let's take a look at the corner case. Okay, this is the corner point, and these are the non-zero x derivative, and these are non-zero y derivative. or perhaps I should use the arrow should point to okay, for this we have non-zero x y derivative, non-zero x derivative. Well, you may observe that when ix are non-zero, when ix are non-zero, for example, for those points, when ix are non-zero, what about the corresponding iy? For example, for the 2 points, their x derivatives are non-zero. However, their y derivatives are 0. And similarly, for the 2 points, their y derivatives are non-zero, but their x derivatives are 0. So if you compute ix, iy, if you compute this, because ix and iy, they cannot be non-zero simultaneously. I mean, one of them have to be 0. At least one of them has to be 0. They cannot be non-zero simultaneously. Can you name a case when they are non-zero simultaneously? You cannot find such case when they are non-zero simultaneously. For example, consider these points. These points have what? They have non-zero, their y derivative are non-zero, but they have 0 x derivative. Well, for these points, their y derivatives are 0. Their x derivative are non-zero, but their y derivative are 0. So for those edge points, for those edge pixels, either ix will be 0 or iy will be 0. So this term ix multiplied by iy will always be 0. Can you get the point? Okay, well, for example, look at this. What happens when ix multiply by iy? You get nothing. Okay, here you have a non-zero, you have non-zero ix. Non-zero ix for the 2 columns. And you have non-zero iy for the 2 rows. But their multiplication just gives you nothing. You can see all the edges for the square, all the edges they just disappear because their ix and iy, they cannot be non-zero at the same time. I mean, either one of them will be 0. Okay. So the multiplication, you can see the edge just disappear after is iy, meaning that this term is 0. Okay. Therefore, for a corner point, for this corner point, we call this a nice case because the edges of this corner, it just parallel with the image frame, with the image boundary. So we call this this is an axis aligned corner. So for axis aligned corner, as we mentioned before, the 2 terms, they are non-zero. Okay. However, for the off diagonal terms are 0 because ix and iy they cannot be non-zero at the same time. Okay, So that's how we tell whether a point is a corner or not. Clear? So for flat region pixels, lambda 1, lambda 2, the diagonal terms, there will be 0. For edge pixels, only one of them is 0. For edge pixels, lambda 1 and lambda 2, for edge pixels, either lambda 1 will be 0 or lambda 2 will be 0. Okay, so there are only one non-zero element for the diagonal terms. For corner pixel, both lambda 1 and lambda 2 are non-zero. Okay, so you can see that's how we measure, that's how we identify whether this pixel is a corner or an edge or just within some flat region. By looking at the value of the second moment matrix M, which is computed by the image gradients within the window. Okay, so this is for a good case. The axis aligned case. Axis aligned means the edges of the corners are parallel to image boundary. So this is an ideal case. What if we have a corner that is not aligned? What if we have a corner like this, whose boundaries are not parallel to image boundary? The image boundary should, for example, this is the image, while the edges of the corners are not parallel to image boundary. What if we have this case? Well, in this case, we can rotate. You can imagine after some rotation, we can make this non-aligned corner to align with the image boundary. Okay, so in this case, the second moment matrix M, for this case, for this is the corner point. Okay, this is the corner point, and we're gonna look at, for example, this window. Okay, this window. Then the second moment matrix M for this window can be expressed like this, where X represents, this X represents the a rotation matrix. A rotation matrix, which means the corner is rotated. The corner is rotated. Okay, so you can imagine initially we have some axis aligned case. Okay, and then we rotate the corner by the rotation matrix. Then this corner becomes, after rotation, then this corner becomes like this. So this rotation is described, captured by the rotation matrix. Okay, anyway, if we have non-axis aligned case, we just look at the eigenvalue. We look at the eigenvalue of matrix M. Okay, we will not dive into details. Within an image, oftentimes we have non-aligned case, right? Basically, almost all the corners are non-aligned. Okay, so we cannot just look at the second moment matrix M. We need to look at its eigenvalues. Eigenvalues because those corners are rotated by some rotation matrix. Okay, we will not explain the details. Why? Because the explanation will involve the algebras, linear algebras, and the rotation matrix. Okay, so when we look at M, we should not look at M itself. Rather, we should decompose M into its eigenvalue representation. And we should look at its eigenvalues. And the eigenvalues lambda 1, lambda 2 will give information about whether it's the cornerness, the corner information of this point. Okay, so lambda 1, lambda 2 here are the eigenvalue of the matrix M. Okay, so this region, when both lambda 1 and lambda 2 are small, it represents the flat region, right? And for lambda 1 and lambda 2 are large, then this represent corners. And the edge pixels are indicated by the green areas where only one value is large and the other is rather small. Okay, and we can design a corner response function with lambda 1 and lambda 2. A corner response function, remember? Remember how we compute the matrix M to get cornerness score, right? For each pixel, we need to compute a value to indicate the cornerness of this pixel. So we need to design a function by using lambda 1 and lambda 2. So this is a sample function. Well, think about that. This value, this f, well, let's see if f is reasonable. If f is reasonable, why f is reasonable? Because f will be large when both lambda 1 and lambda 2 are large. We can see this by, for example, we can divide it. This term is equivalent to what? So we divide the numerator and denominator by the same term, lambda 1 and lambda 2, right? So this is equal to lambda 2 plus lambda 1, right? So when both lambda 1 and lambda 2 are large, then this term is pretty small, right? And then this term will be large, f will be large. And when both lambda 1 and lambda 2 are small, then this term will be large and f will be small. And similarly, if either one of them are large, then this is for the edge case, it's in between. It's in between because lambda 1, if lambda 1 is pretty large, then this term is close to 0, and lambda 2 is close. If lambda 2 is small, then this term is quite large. Okay. So the design of the cornerness score function is not unique. This is just an example. This is just it's just one choice of the coordinates function. Okay, you can design other coordinates response function as long as it's reasonable. Okay. Okay, now let's take a short break, 10 minutes break. Let's come back at 8:30, okay? All right, let's continue. So up until now, we have explained how to do edge detection and corner detection. You know, corners are consist of two edges, right? So both edge detection and corner detection involve the use of image gradients. So I hope now you can appreciate image gradients as fundamental tools for image processing. Okay, it can be used in many important tasks, and it can capture important properties, image properties. Okay, now back to corner detection. And as I mentioned, this function is just one alternative. It's just one way to compute cornerness score. And there are other alternatives. For example,
呢個係你
I think it should be this one. Corner detection. There are other derivatives or other alternatives.
Close to the origin in this space, you essentially are a flat region. And if you happen to lie in this region, where lambda 1 is much greater than lambda 2, it's an edge. If you're in the blue region, where both are significant, then you might call it a corner. So we want to come up with a very simple way of doing this classification, and that's what the Harris corner detector does. Essentially,
For example, this is another alternative function for computing the cornerness score. Lambda 1 times lambda 2 minus k lambda 1 plus lambda 2. Well, k is just like some hyperparameter which you can decide.
what Harris has done is come up with an expression here where he maps lambda 1 and
So you can see this is the visualization. So if there's a point here, its R value should be large. Okay, if the point is here, in contrast, if the point is here, both lambda 1 and lambda 2 should be small, and hence the R value is small. So this is the visualization of the R value or the cornerness score, or equivalently F, the F function.
lambda 2 to a single number r. So this is an empirically determined function, lambda 1 times lambda 2 minus k times lambda 1 plus lambda 2 squared, where k is also empirically determined. When you plug in lambda 1 and lambda 2 here, you get r, and r is being plotted here in this image.
So this is just another way to compute cornerness,
where the brightness of the point is proportional to r. So what's nice about this space is that if you now use a threshold, you apply a threshold to r, each threshold corresponds to this kind of a curve.
So for example, okay, we compute for each pixel, we compute R, right? And then we set a threshold T. And those are for those pixels who has values, whose cornerness response larger than some threshold, then we consider they are corner pixels.
In lambda 1, lambda 2 space. And so you can say if you happen to be in this region, that is r is above the threshold, you're likely a corner. If you're below the threshold, then you're not a corner. So it's that.
This line represents when this function equal to t, points on this line represent those points whose corner response equal to some threshold t. Okay.
That's simple. So let's see how this works. So here you have a very simple image, admittedly, BBC, and you apply Harris corner detection to it. And this is the value of R that you're looking at on this side. So the R goes from dark values, so black represents very low values of R, white is large values, and you're going through shades of red and yellow. And you see that essentially at the corners, you see very large values right here. Now, one of the problems with corner detection, and this happens with feature detection in general, is that when you look at the corners, at the points where you have these strong responses, you're going to get clusters of points.
Clusters of points, multiple points for one region, cluster of points. And that's why we need to do non-maximum suppression.
That have large values. And you need to decide which one is the peak. So this is quite natural. So in this case, you get all of these very bright values, and that's because you're very close to a corner. So that says that we really need to find the peaks, and the peaks would then correspond to the corners. This again is a problem that appears in many different domains. It's peak detection. And the method we're going to talk about now is useful in all of those different domains, and that's called non-maximal suppression. So the idea is extremely simple. It is to take a little window, and you're going to slide this window over the image.
So this window is represented in white. So this white window, okay, and this is the center of the window. So we can perform non-maximum suppression by comparing whether the center pixel is larger than the rest of pixels. So if the pixel at the center is the maximum value, then we keep it. Otherwise, we may suppress it, discard it, or diminish its value. Okay? For this case, clearly, this is not the center is not the largest. It's not the largest. So we just suppress it. We don't need to pay attention to it because it doesn't have any value. Well, for this case, okay, the center pixel, the value of the center pixel is less than this one, is smaller than this one. So we simply suppress this, discard this. Okay, and then when we move the window to this position, to this pixel, and it happens to be the largest one, then we keep it. So we do this iteratively, and eventually all these pixels will be set to 0 because it's not the largest. We either set them to 0, discard them, or we can diminish its values. So normally we just set them to 0, as what we do in what's the name for the edge detection method? For the edge detection, what's the name? Louder, please. What's that? The edge detection method. You know, we have Sobel, right? But Sobel has some limitations, and what's the name of that? Canny. Okay, Canny, right? Just as what we do in Canny edge detection. Now maximum suppression, only keep the peak value and set the other ones. If it's not peak, set them to 0.
In this case, the image is the image R, which is the response to the corner detector. And at each position, if the pixel at the center is the maximum value, then you simply retain it. If it's not the maximum value, which means there's some other pixel in that tiny window that's actually has a larger value, then you either suppress it, you diminish the value, or you essentially eliminate it completely. So that's how this works. So in this case, this point is clearly not a peak. This point is not a peak because this point is brighter, so you might just eliminate it or you might suppress it, and this one happens to be a peak. So this way you can find the peak with one scan of the image. All right, so once you've done with that, then you end up with your corners, and here are the corners overlaid on the image that you started.
So these are the corners overlaid, depicted on the images.
Off with BBC, and you see that more or less the corners are in all the right places. You do say some things, some corners right here detected which may or may not be deemed as corners, although they have very high curvature here, but otherwise you get good results. But admittedly, this is a very simple image. So let's take a look at something a little bit more challenging. This is a printed circuit board, and you have lots of corners in this case. And once again, you have your R image, which is computed using the technique we described. This is after thresholding the R image, and then after applying peak detection using non-maximal suppression, you get these corners right here. If you take a close look at these, you see that we've done pretty well. There are a couple of corners, like this one right here that's missed, and maybe this one right here. But by and large, the corners have been detected quite well. Now, since we're talking about corners, let's end with an illusion that's related to corners. So this has more to do with us, the human visual system.
So this is an interesting phenomenon about our human visual system.
So here you see an image, a checkerboard-like pattern, but when you look at it, you see that the center of the pattern actually bulges.
So that's when you look at this image, you can is there a bump here? Can you see a bump here? A bulge, right? Right? Well, actually, this is an image of a chessboard. So there shouldn't be any bump
in this area right here. And you see that the pattern has a lot of these tiny little dots or squares, white dots and black dots that are placed strategically close to the corners of your.
So these little squares, white squares, black squares, they are placed purposely at this position to create this illusion. There's a bump, but actually there are no bumps here.
Your checkerboard pattern. And if you remove these tiny little squares, you see that indeed you have a perfect checkerboard pattern.
Okay, so these little squares will create some illusion.
All the lines are either parallel or perpendicular to each other. If you introduce the squares, the tiny little squares back, you see the bulge once again. So this is interesting. It turns out that by placing these tiny squares close to the intersections in the main checkerboard.
So they are placed purposely at the intersection. This place, okay, at the intersection.
Pattern, you're actually biasing the human visual system to believe that the corners are at slightly different locations than they actually are. These are some of the biases that are inherent to the human visual system that leads us to this conclusion that there's a bulging happening in the center of the image. Once again, the punchline is we're not perfect.
Okay, now back to the Harris-Quinn, the algorithm. All right. Now we know what the M is. What M is? That is, we place a window at each pixel, and we look at its second. We examine the second moment matrix M, which characterize which is characterized by the second moment matrix M. In the good case, axis-aligned case, characterized by the lambda 1, lambda 2, and those are correspond to IX, IY. Okay? Characterized by X derivative, Y derivative. Okay, so we can compute their coordinates score using some function f or r in the video. Okay, you can design such function as long as it's reasonable. Okay, so we compute the coordinates map and then we threshold it by only keep the larger response. And then we do non-maximum suppression to take the points of local maxima, to take the peak values. So this is our final result. And if we draw the corner points, overlay them along the image, and you can see, for example, at these regions, similar points are identified. Well, notice that the two images they are under different illumination, and also the objects have different orientation. They have different orientation. Yet you can see same corner points have been successfully identified, which demonstrating that Harris corner detection is rotation invariant. Rotation invariant. Well, these points are not identified on this image because the viewpoints are different. The viewpoints are different. So so that's reasonable. Okay. So I would like to emphasize. So look at this region, and you can see same corner points are identified despite the differences in their orientation. This shows that Harris corner detection algorithm is rotation to is robust to rotation. It's robust to rotation, which can also be shown. We can also tell it's rotation invariant from this, because for the good case, for the axis-aligned case and the non-aligned case, they are only up to the difference between them is up to a rotation matrix, while their lambda 1, lambda 2, they have the same lambda 1, lambda 2. The differences are only up to a rotation matrix. So that's why Harris corner detection algorithm is robust to rotation. I have skipped a few slides here. I have skipped these few slides because they just illustrate the property, the visualization of the E function. Okay, so what the E function would look like if it's edge, if it's a flat region or a edge line or a corner. So I'll just leave them for your reference. Okay, now so we have shown Harris corner detector is rotation invariant. So rotation is a one geometry change. Okay, so scaling is another geometry change, geometry transformation we mentioned. Is it scale invariant? What does it mean by scale invariant? when we do corner detection, we slide a window of fixed size across the image, right? A fixed window, a window with a fixed size. Of course, we have to determine the size of the window first, and then we apply it to scan the image, right? So the question is whether a window with a fixed size can be applied to identify corners of varying sizes. For example, we have two corners here. We have a small corner and we have a large corner. Can the blue window be applied to detect both the small corner and the large corner? So apparently, if we apply the blue window is suitable for detecting small corner. It's suitable for detecting corner of this size. Okay, but if we apply it on this large corner, if we apply it on this large corner, the window is too small. The window is overly small. If you slide the window along the corner edge, along the edge of the corner, the changes within the window will not be will not be like this, because the window is too small, and if you slide it along the edge of this big corner, we will have, you know, the M matrix. The M matrix will be like there's only one lambda will be large, and the rest will be small. Because the changes within the small window is just like you sliding them. It cannot capture the content of the corner. Well, simply put, if we want to capture small corner, you should use a small window. And if you want to identify large corner, you should apply a large window. So you should apply proper size of window to capture the corners of varying sizes. Okay, so within an image, there are many corner points. There are small corners, medium corners, and large corners. We cannot identify all the corner pixels using a fixed window. Then what should we do? The solution is just to apply a series of windows of varying sizes. Okay, for example, we may consider applying multiple windows of varying sizes. Okay, and then so previously for each pixel, we only evaluate one window. We only evaluate, we apply a fixed window size. Okay, previously, for example, we only use, for each pixel, we only examine this window. However, because we do not know the size of the purple window to apply. We may consider a series of windows. So for each pixel, instead of looking at just one window, now we look at 1, 2, 3, 4, 5, 6. We look at 6 windows of different varying sizes. Okay. 1, 2, 3, 4, 5, 6. For each pixel, we consider 6 windows. And then what? 1, 2, 3, 4, 5, 6. Well, let's take a look at these 2 cases. Okay, and let's see which window is appropriate. For the left image, which window is most suitable for the left image? Well, perhaps the red one, or the largest one. Okay. Well, we can compute some function f. So the f function, it can be the corner response function. It can be the corner response function we designed before. So we need to design an appropriate function f. And this function f, it will give the largest response with the proper window size. Okay. So there are, for example, 6 window size. 6 window size. And so for example, we have 6 window size, 1, 2, 3, 4, 5, 6. And the largest response occurs at window 5. Okay. And for this image, the largest response occur at 1, 2, 3, 4, 5, 6, occur at the window 2. Okay. So if we have a suitable, appropriate function f, and this function f is very nice. It can achieve maximum response. It can achieve maximum response with the best window size, with the most suitable window size. Okay. And suppose our f, our previous f, the corner response function is such a good function. It's such a good function. Then we can use it, the corner response function, to identify the proper window size for this pixel. Okay. So the solution is to apply multiple window at one pixel. That is to look at a window of different scale, to look at the image content at a different scale, and select the window that gives the largest response, that generate the largest response. Okay. So we can achieve automatic. Scale selection. So we can apply a proper window size, appropriate window size for different image patches at a different scale. So, well, this assumes that we have such a good function f. It assumes that we have such a good function f, and this good function f will help us to choose the best scale, the best window size, the best scale or the best window size. The function f is appropriate. The function f is well designed such that when the scale is right, when the size is right, you will achieve maximum response. Okay, so when the size of the window is the best fit for the corner, then you will achieve maximum response. And similarly, for this window, if this window size is the most appropriate for this small corner, then you will give maximum response. Okay, so this can achieve automatic scale selection. Okay, so let's say we have a very good function f, and we look at the scale at which this function f achieves the maximum value. Achieves the maximum value. For the right image, for the left image, this is the this is the scale. This is the scale that it achieves the maximum value. This scale, this one. Okay, and for the right image, it achieves the maximum value at a larger scale. So this is on the scale. This scale is larger than this one. Okay, so the idea is just to look at the scale space, applying windows of varying sizes. In this example, we apply windows of, we increase the window size. And we increase the window size. So we are given a function f. Okay, so we draw a curve for each window size. We compute the value for f. See, we update the f function for different window size. Okay, and so you can see the curves looks different. The curves are different, and they achieve the maximum value at a different scales. The interesting thing is the maximum value is achieved at the best window size. For this image, the most appropriate scale for this point is represented by the yellow window. Okay, and for the right image, the best scale is also represented by the yellow window. Okay, so we need such a function f. The function f is very carefully designed such that it will generate maximum response when the scale is right. When the scale is right for the key point. Okay, so now I'm going to introduce such function, such carefully designed function for blob detection. And the few slides, these few slides are for your reference. So first derivative, second derivatives, and one-dimensional Gaussian and derivatives. So I just show them here if you need to, if you need a relevant background. Okay, so I'll leave it. I just leave it. Okay. Now I'll introduce the LOG function. The LOG function is the function we want. The LOG function can gives maximum response when the scale is right. Okay, so what is LOG? LOG represents Laplacian of Gaussian, and you might have noticed that Gaussians are everywhere. The Gaussian function, okay, Gaussian smoothing, derivative of Gaussian. Now we have Laplacian of Gaussian. So the Gaussian function is really useful, just like image gradient. Okay, we can apply Gaussian function for smoothing, Gaussian filter for smoothing. Then we can apply derivative of Gaussian for what? For edge detection. Now we apply Laplacian of Gaussian for blob detection. So the Gaussian function is magical. Laplacian of Gaussian can be computed by second order derivatives. When we do edge detection or corner detection, we apply first order derivatives. Okay? But here, Laplacian of Gaussian involved the computation. It involved the computation of second order derivatives. The second order derivative of the Gaussian function. Anyway, LOG looks like this. And Gaussian looks like this. Gaussian looks like this. You can see the peak is at its center. The center is the peak. And then the value just diminish quickly with respect to inversely proportional to the distance. What can you observe for the LOG function? When are the maximum value achieved? And at which place the lowest value achieved? At the center. The lowest value is at the center. Okay? While the maximum value is achieved along this circle. Okay? Can you imagine why this function is appropriate for blob detection? Can you see a blob here? There's a blob here. Okay? But you may say that there's also a blob here. But why can we apply Gaussian? Instead, we need to apply Laplacian of Gaussian. So Laplacian of Gaussian, this is the Laplacian filter. This is the Laplacian of Gaussian filter. So I put them here for your reference. Well, this is the Laplacian of Gaussian function. Okay, suppose we have a blob image. Remember, the definition of blob is just areas which are brighter or darker than surrounding areas. Okay, so apparently this is a dark blob. It's darker than its surrounding areas. Okay. So this function, this LOG function, well, this is just a slice of this LOG function. Okay, this function will achieve maximum response when the zeros of the Laplacian, what are the zeros of this Laplacian? Guess it should be here. The zero. This is the zero. The zero of the Laplacian. So this LOG function have a very nice property that the maximum response occurs when the zeros of the Laplacian align with the circle, meaning that this is R. This is the circle. Okay, so this is R. When the zeros of the Laplacian align with the circle, then you will achieve maximum response. This filter will achieve maximum response. Now, where are the zeros? This is the LOG filter. The zeros are, this is the zeros. Okay, so for this filter, if you happen to have a blob of this size, then this filter is perfect for identifying blob of this size, because you will give maximum response. Of course, the LG, we can have a set of LG filters with different sizes, sigma, and they will look different. So this is just an example of LOG filter with some sigma, with a certain sigma. The sigma value determines the size of the Gaussian kernel. Okay, and you can see the zeros are around this circle. Okay, so the LOG function will give maximum response when the if the blob has the size of the blob align with the zeros. Okay, so this filter for blob size, for blobs with this size, then this filter is perfect for blob of this size. If you apply a smaller LOG filter, you will not get a large response. Okay. Well, let me put it this way. Now we have blobs of different sizes, right? We have a tiny blob, and then we have a medium blob, and then we have a large blob. How can we identify all those blobs simultaneously? You cannot apply a single LOG filter. You need to apply a series of LOG filter with different sizes. Okay, this is similar to increasing the window size in corner detection. You applying filters of varying sizes, and the filter, and for blobs of different sizes. For blobs of different sizes, the most suited filter will generate largest response for the corresponding blob. Okay, so for example, for the tiny blob, for this tiny blob, the second filter will give maximum response. Well, for the medium blob, the third filter will give maximum response. Well, for the largest blob, the fourth filter will give maximum response. Okay, that's because this image, the size of this image align with the zeros of this filter. It's like they are perfect. They are a perfect fit to each other. So this filter is perfect for identify blobs of this size. Well, this filter is perfect for identify the medium blob. And this filter is perfect for identify the tiny blobs. That's why we need to apply a set of filters simultaneously. Okay, so that is the idea behind SIFT detector. So how can we achieve scale invariant? Achieving scale invariant means that we can identify blobs of varying sizes simultaneously. For example, the sunflower images. There are many sunflowers of varying sizes within these images. How can we identify? How can I identify these blob-like shapes simultaneously? It's not enough. It's not, you cannot just apply one filter and expect to identify blobs of different sizes, because a small blob can only identify a small filter can only identify tiny blobs. You only achieve maximum response for those blobs that align with its zeros. Can only identify small blobs. Okay, you can see the response. And similarly, median filter can only identify medium blobs. Okay, so if you want to identify all the blobs together simultaneously, you need to apply filters of different sizes. Okay, which means for each pixel, you need to consider the response of multiple filters of varying sizes. And then you can determine, and then you can see for each pixel, you need to consider the response of multiple filters, and then you pick the one that gives maximum response. For example, this one, this gives maximum response. And then this is the proper scale for this blob. And for this one, this gives the maximum response. Then this is the the size of this filter represents the proper scale for this kind of for the medium blob. And similarly, this is the proper scale for this blob. Okay, so that's the idea behind blob detection or SIFT detection. Okay, and the log function is the desirable function, is the carefully designed function. So this function has the very nice property such that the maximum response occurs when the zeros of the Laplacian align with the circle. And this can help us to select the appropriate scale as well as the filter. Okay. Another example is this is the log response with sigma 2. So this is a small filter. The small filter, let's look at the y points. The y points that has the largest brightness value. Okay, can see this is the y points represent maxima. Okay, and the black points represent minima. Okay, and this one, the y points represent the center. The y points here. Okay, it represents the the maxima value when log sigma being 2. Okay, when sigma being 10, you can see a large filter with a large filter, the maximum point is achieved at this place. When log, the sigma being 2, the maximum point is achieved at the eye region of this person. Okay, so the scale is different. When smaller sigma, this helps identify this blob, the eye. With large sigma, it helps us to identify the head as an interesting point. Head as a blob, this blob. Okay, small sigma helps us to identify the eye region. Okay, I'll just stop here and let's talk more next week.